Let's do an example problem with the Gibbs isotherm. So suppose we measure the surface tension of a solution as a function of concentration. So we have surface tension, and we're going to plot the log of the concentration. We typically find data looks something like this. First, the concentration is so low it doesn't change anything, and then we get a linear curve, and then a flat spot, sometimes. So what's going on here? Well, here, this part of the curve, all we have going on is adsorption, which we're going to model with our Gibbs isotherm. Over here, it looks like we're adding in more surfactant, yet the surface tension's not going down. And the reason for that is over here, we have adsorption still. But competing with it, we have micelle formation. So when we use the Gibbs adsorption isotherm, we're going to apply it to this part of the curve and not to the flat part. Okay, so really, we're just talking about this right now. We take the slope of the curve and we find that it comes to a -10 millinewton per meter. How can we analyze this data? Well, remember the Gibbs isotherm says that we have the slope of the surface tension with the log of concentration is going to be negative of the surface excess times RT. Suppose we're given that this is a non-electrolyte surfactant. So we don't have to worry about how many pieces it breaks into. It doesn't break down into pieces. So we just have this simple equation here. So the surface excess, we can see, is just going to be the slope, the negative of the slope, divided by RT. So suppose we collected this data at 25 degrees C. So we have that too. Okay, so we want to put everything into SI units. So the surface excess is the negative of the slope. So we have a positive 0.010 newtons per meter divided by 8.314 joules per mole per Kelvin and 298 kelvins. Oops, kelvins. Okay. So the surface excess comes to 4 times 10 to the -6th. And if we cancel our units here, we can see kelvins will cancel kelvins, and we'll end up with moles per meter squared. If we remember that a joule is just a newton meter, so newtons cancel, we're left with 1 unit extra of meters, so we get meters squared. So it's especially interesting to look at this section of the curve here where the slope is constant. So if we take the reciprocal of our surface excess, so we've got 1 over 4 times 10 to the -6 mole per meter squared, we're going to get units of meters squared per mole. So this is sort of the size of a molecule. And we'll see that that is equal to 250,000 meters squared per mole. And what's really interesting is to put this in the size of molecular dimensions. So let's get rid of moles. So we know that for every 1 mole, there's 6.02 times 10 to the 23rd molecules of surfactant. So we can cancel our units of moles. And then let's put that into something molecular sized instead of meters. So let's get rid of meters and go to angstroms. So want to get rid of meters squared, so 1 meter squared is 10 to the 20th angstrom squared. And so we cancel our meters squared. And when we do this, we end up with about 40 angstrom squared. So that's giving us how much space each surfactant molecule has when it moves around on the surface. So it's sort of giving us an idea of what the molecular picture is once we've figured out how many excess surface molecules are at the surface.